In the last lesson, we detected lines from a series of points in the gradient image using the Hough transform detection algorithm. We then took these lines and placed them on a blank image, which we then merged with our color image, ultimately displaying the lines onto our lanes. What we'll do now is further optimize how these lines are displayed. It's important to first recognize that the lines currently displayed correspond to bins which exceeded the voting threshold. They were voted as the lines which best described our data. What we'll do now is, instead of having multiple lines, we can average out their slope and y-intercept into a single line that traces out both of our lanes. Before getting into it, it seems that there is some inconsistency in the code. This should be image, so as to properly reference the argument, not lane image. And the same thing here. Make sure to reference the argument image, not the global variable canny. It shouldn't have made a difference since they both correspond to the same value. The same case for this one, but it's always good to be consistent so as to avoid bugs. Also, not a good habit to reuse variable names, so we'll rename this to canny image and change it over here accordingly. All right, we'll start this lesson off by going over here and setting averaged lines is equal to the return value of some function that we'll declare later on, average slope intercept, that will be our function name, and we'll pass into it our colored lane image as well as the lines that we detected. And now we'll simply define the function right on top, def average slope intercept with argument image and lines. And what we'll do first is we'll declare two empty lists. Left fit is equal to an empty list. Right fit is also equal to an empty list. Left fit will contain the coordinates of the averaged lines on the left, and intuitively, right fit will contain the coordinates of the line which will display on the right. What we can do now is loop through every line as we did previously, for line in lines, and reshape each line into a one-dimensional array with 4 elements, line.reshape 4, and now we'll unpack the elements of the array into 4 variables, where x1, y1, x2, y2 will equal the 4 values in the array respectively. Nothing new so far. These are the points of a line. When you're given the points of a line, it's very easy to compute the slope by calculating the change in y over the change in x, subbing that into our equation to then determine the y-intercept. Well, to determine these parameters in code, what we can do is set parameters is equal to numpy.polyfit. What polyfit will do for us is it will fit a first-degree polynomial, which would simply be a linear function of y is equal to mx plus b. It's going to fit this polynomial to our x and y points and return a vector of coefficients which describe the slope and y-intercept. The first argument is where you will place the x coordinates of your 2 points, x1, x2. The second argument is where you will place the y coordinates of your 2 points, y1 and y2. And we'll fit a polynomial of degree 1 to our x and y points. That way we get the parameters of a linear function. If you go ahead and print parameters into our terminal, pythonlanes.py, for each line that we iterate through, it prints the slope and the y-intercept. The slope is the first element in the array. The y-intercept is the second element. So what we can do is set slope is equal to parameters at index 0, and we'll set intercept is equal to parameters at index 1. And now for each line that we iterate through, we need to check if the slope of that line, does it correspond to a line on the left side or a line on the right side. To determine this, it's important to note that our lines, depending on which side they're at, are all roughly more or less going in the same direction. All the lines here are slanted a bit to the left, and all the lines here are slanted a bit to the right. Here's our image displayed with x and y axes. Notice that in the image, the y-axis goes downwards along the rows. And if you remember from basic high school math, a line has a positive slope when y always increases as x increases. So these lines would have a positive slope as their change in y over the change in x would result in a positive value. Although for these lines, since as x increases, y decreases, their slope value would therefore be negative since their change in y over the change in x would result in a negative value. Final conclusion being, lines on the left will have a negative slope, lines on the right will have a positive slope. So what we can do is, back to our code, we can write if slope is smaller than 0, if the line we're iterating through has a negative slope value, we'll append it into the left list, left fit dot append, and we'll append each slope and y-intercept as a tuple. Slope, intercept. Otherwise, else, we'll append it into the right list. Right fit dot append slope and the y-intercept. If we print the results outside of the for loop, print left fit, print right fit, back to our terminal, python lanes.py. Now we have a list that contains all of the slopes and y-intercepts of the lines on the left side, and another list that contains all the slopes and y-intercepts of the lines on the right side. What we want to do now is average out all of these values into a single slope and y-intercept. Back to our code, we'll do that for both sides, but we'll start with the left side. We'll set left fit average is equal to numpy.average, and we're going to average out all the values of our left fit, and it's really important that you specify an axis is equal to 0. Imagine this was an array of multiple rows and 2 columns. What we want to do is operate vertically along the rows to get the average slope and the average y-intercept, respectively. Do the same thing on the right side. Right fit average is equal to numpy.average. We'll do that for right fit with an axis is equal to 0. All right, we'll go ahead and print left fit average, print right fit average, and we'll go ahead and just label them for clarity, left and right. Back to our terminal. We get back to arrays. This array represents the average slope and y-intercept of a single line through the left side, and this array, the average slope and y-intercept of a single line through the right side. We're not out of the woods yet. We have the slopes and y-intercepts of the lines that we'll eventually draw, but we can't actually draw them unless we also specify their coordinates to actually specify where we want our lines to be placed. The x1, y1, x2, y2 for each line. So what we'll do is we'll define a function, def make coordinates, with argument image and line parameters with some return value. This return value is going to denote x and y coordinates of the line. So back here, we'll set left line equal to the return value of make coordinates. We'll pass in the respective arguments, the image, as well as the slope and y-intercept of our left line, left fit average. Same thing for the right line is equal to make coordinates, image, right fit average. Back to our function, we're going to unpack this list of 2 elements, whichever one that's being passed in, the slope and intercept into 2 variables. Slope intercept is equal to line parameters. We'll start with y1, the initial vertical position of our lines. This one is pretty obvious since we want our lines to start at the bottom of the image. Before we do this, if you go ahead and print the shape of the image, print image.shape into your terminal. We'll rerun this code. It prints twice since clearly we're calling the function twice, but regardless, recall that the shape corresponds to your array's dimensions. In this case, this represents the image's height, width, and number of channels. We're only interested in the height, which also corresponds to the bottom coordinate of our image, as demonstrated by matplotlib. A little counterintuitive that the highest value is on the bottom of the y-axis, but another way to interpret this is to have the y-axis going vertically downwards from 0 to 700, which makes sense since images are simply arrays of pixels and array indices are read from the top down. We'll set y1 is equal to image.shape at index 0, since that represented the height. And now y2 is going to equal y1 times 3/5. We'll make this into an integer type. And so essentially this will be 704 times 3/5, which is going to evaluate to 422, which means that both of our lines will start from the bottom at 704 and goes 3/5 of the way upwards up until the coordinate 420. All right, now x1 can simply be determined algebraically. We know that y is equal to mx plus b, so x is equal to y minus b divided by m if you rearrange the variables. So we can simply set x1 is equal to y1 minus the intercept divided by the slope. We'll make this into an integer as well. And the same thing for x2, except that we have to replace this with x2 and y2. Now that we have all of our coordinates, we'll return them as a numpy array, numpy.array, x1, y1, x2, y2. So both of our lines are going to have the same vertical coordinates. They're both going to start at the very bottom. But they're going to start at the bottom and go upwards 3/5 of the way up until the coordinate 424. But their horizontal coordinates are obviously dependent on their slope and y-intercept, which we calculated right here. We finally have our lines. We can return them as an array. Return numpy.array left line and right line. And now comes the fun part, which is instead of our line image being populated by the Huff detected lines, we're going to pass in the averaged lines. If we show the line image instead, run the code, this looks a lot smoother. Instead of many lines, they were all averaged out into a single line on each side. Back to our code. Obviously, we're still blending the line image with the color image. So let's show that instead. Combo image. Back to our terminal. We'll rerun this. And it displays our two lines. On our two lanes, we took the average of our lines and displayed one line on each side instead. This looks a lot smoother than earlier. One more thing before we end this lesson is that previously we were passing in a three-dimensional array, the Huff lines, into our display lines function. But now we're passing in the average lines that we created, and we know that when we iterate through over this lines array, each line is already a one-dimensional array, so there's no need to reshape it into one. It already is one-dimensional, so feel free to remove the reshape for. It's just extra code. It doesn't really make a difference whether you have it or not. And better yet, we can simply unpack each line into 4 variables over here and delete that. And that is all. Let's rerun it to make sure we didn't make any mistakes. And everything still works out accordingly. In the next lesson, we'll use the code that we currently have and take it up a notch by identifying lane lines in a video.